Good evening, everyone. Today we'll be doing our predicting abalone age using machine learning. So from smarter harvesting for a sustainable future. So traditionally, estimating the age is done by cutting the shell and counting the number of rings, which is very time consuming and invasive. So some of the applications for abalone age include marine biology and environmental science, like determining suitable harvesting times as well as to understand the population. So instead of cutting the shell, we will be using machine learning models to estimate abalone age from physical measurements. So here are some of our algorithms we will use, including linear regression as our baseline model, which is easy to interpret, followed by decision tree as well as random forest, which are our non-linear models.
Okay, so for the first model is the linear regression. It is a simple model trained using stochastic gradient descent to find a direct relationship between the features and the target. The advantage is easy to understand and works well even with large data set and making it a baseline model for comparison. However, it can't capture complex nonlinear relationship and it's quite sensitive when features are highly related. Next. So for the decision tree regressor, it is non-parametric model that split the data into smaller group based on feature values. The advantage is can learn complex nonlinear patterns and is very easy to visualize. It also doesn't need much data preparation. But for the disadvantage is it can overfit easily, especially when the data is noisy. So for the random forest regression, it is an ensemble of multiple decision tree trained on random data and features. The advantage is help to reduce overfitting and makes the model more stable and it works well even when the data has noise or many features. However, it comes with a higher computational cost and is less interpretable.
We balance bias and variance across models. Linear regression is simple but may underfit. Decision trees capture non-linear patterns but can overfit, and random forest average many trees for better stability. These theories guide our preprocessing and model choice. Linear regression sets a baseline, decision trees explore complexity, and random forests give the most reliable predictions leading into our evaluation results.
After loading the dataset, we first explore and visualize the features to check what data we had, confirm there is no missing value. So for Avalon, we add about 1.5 years because Avalon don't form a clear ring during the 1.5 years. So this will give us their true age. From the graph, most features look normally distributed, but you can see from the height, features show a potential outliner. So we need to remove it.
From the heat map, we can see how closely two attributes are correlated. From blue boxes indicate low correlation and can be excluded during pre-processing. And the closer the color is to red, the higher the correlation, which is important for training our model. However, correlation doesn't capture non-linear relationship and is sensitive to outliers. So we can look at other features to improve the prediction. Next. This slide shows the scatter plot of each numerical feature against age. The red line indicates the trend. As you can see, most features like whole weight and diameter have a positive linear relationship with age. This support using linear model and help in choosing the relevant feature for regression tasks. In this step, we prepare our data for modeling by using stratified sampling to split the data into 80% training and 20% testing. Then we build a pipeline to pre-process this feature. For numerical feature, it was analyzed using G-score scalar, while category feature like male and female was encoded using one-hot encoding. Then we combine those features using column transformer. Next.
We began by training three regression models: SGD regressor, decision tree regressor, and random forest regressor. Each was built using a pre-processing pipeline and evaluated with 5-fold cross-validation to get reliable Rs and scores. From the first run, random forest showed the lowest and most stable RMSE, meaning it performed best overall. Next, we fine-tune our models. We first create a baseline model to compare performance. Then we define a hyperparameter grid, testing different learning rates, depths, and also regularization strengths. And we also use randomized search CV to find the best parameter combinations. Finally, we trained each model using the best parameters and threefold cross-validation. We also plotted training vs validation RMSE to check for overfitting. These help us identify the points where model complexity starts to hurt accuracy, ensuring we choose models that generalize well.
Okay, so for this slide, show the result of our three models. Random forest give the best performance with the lowest RMSE 1.998 and the highest R-square of 0.599 because it's reduced overfitting by combining many trees. The linear regression comes next with RMSE 2.026 and R-square of 0.587. It captures the main linear trend in the data. So for the last, the decision tree performs the worst with RMSE 2.170 and R-square of 0.526 as easily overfit and give higher error. Overall, both random forest and linear regression reduce prediction error by around 36% from the baseline. We look at the linear regression learning curve. So for the left is the regularization curve. The blue line show the training RMSE and the orange line show validation RMSE. Both lines stay close to each other, showing the model generalized well. On the right, the predictor versus actual plot show most point near the red line, meaning the prediction are quite accurate.
The underlying assumption for linear regression is that age can be predicted by estimating it as a weighted sum of the input features, treating each feature as contributing additively and independently to the prediction. The underlying relationships in dataset fit well with the assumption, having a strong R-square and feature correlations from heat map with clear linear trends in plots. Linear and gradient-based learning methods are sensitive to feature scale, which would cause unstable updates as the gradient for one feature could be significantly higher due to its magnitude. This can lead to suboptimal models. Thus, normalizing all features helps to keep the coefficients comparable in magnitude, ensuring that regularization works fairly and gradient descent can update the weights smoothly. With good data to feature ratio, it helps to reduce variance as it provides enough evidence for model to estimate coefficients. Decision tree works by recursively partitioning feature space, selecting splits that minimize Poisson deviance. It captures non-linear interactions unlike linear regressions, such as Abalone age increasing with diameter up to a point before plateauing. Hyperparameter tuning increases performance by creating a balance that captures complex patterns without oversimplifying and preventing overfitting on small groups. The decision trees favor a single feature per split, ignoring overlapping information. Highly correlated features such as abalone length, height, and weight can lead to suboptimal splits. When undergoing training data splits, different trees may be produced, and with the lowest R-square, only roughly half the variety of age can be explained. A large gap between training and validation RMSE against tree depths shows a strong sense of overfitting, therefore making this the worst performer.
As you can see, random forest actually outperformed the other models. It reduced variance using bootstrapping and random feature selection, which helped with our highly correlated feature. And its averaging effect across tree also lower overfitting, shown by the stable validation RMSE. Lastly, it captured non-linear pattern, giving a slight improvement in RMSE and a better R2 score. Next. This slide shows the top 10 features contribute most to the random forest prediction. Shall we stand out as the most important predictor, accounting for nearly 70% of model decision making, followed by strike weight, whole weight, and visceral weight. As you can see, all features are related to the physical size and mass of the abalone. This aligns with biological intuition as larger abalone are typically older. By understanding feature importance, we gain transparency into model and confirm its learning meaningful patterns. Next. So this project explored three machine learning models to predict abalone age. We observed that random forest achieved the best overall performance, while abalone growth patterns are largely linear models. Models non-linear interaction exist that example model like random forest can better capture, making it the best for age prediction. It's offer the most balanced trade-off between bias and variance, making it the most suitable model for age prediction. Future work could include expanding the data set or applying advanced example method to enhance accuracy. Okay, thank you.